Hi, this is Christopher Boucher, and I'm going to explain how to do a exponential probability distribution example. And this example is the second of the examples that I've done. The first one had the same units, meaning the time period or the interval that we're looking for was in the same units as the lambda value. So go back and take a look at that video if you haven't seen that video first, and if exponential probability distributions are tricky to you, or you just want to brush up on them before this one. Okay. Customers arrive at a local ATM on average of 15 people per hour, and they follow the exponential probability distribution. What is the probability a customer will arrive in? And then we have three separate question parts here. So the first one is in 3 minutes. So it's the probability that somebody will arrive in 3 minutes. Okay, so I do this a little bit differently, and that's because when I do the calculations, I don't go and break down lambda down to the units of the time. I go and leave lambda in the units of the that lambda is presented in. In this case, it is given to me as 15 per hour. And then for this question, we're dealing with minutes. So we have a conundrum, you might say, between hours and minutes. And a lot of textbooks will have you convert the lambda down to, say, in this instance, they would say convert it down to the minutes and then multiply it by the minutes. Well, depending upon, there's a lot of different ways that you can solve this problem, but I recommend doing it a little bit differently, and I have a reason why, which I'll show you too. I have a table that's set up, and it shows the relationship between the different units, and it'll make a little bit more sense to you. So let's go and write out what equation I'm going to use for this. I'm going to do it like this. And we use this equation when it is a 0 to a number. So 0 to a number, we use the 1 minus the e, then the negative exponent. And this is where mine might be a little different, but I'm assuming that I'm not the first to just format exponential probability distribution questions like this. It's not too creative. And this is my lambda. Sorry, that back in there is hanged out. So what we have here is we have the time component, and then we have the unit component, and this is the conversion part. So because our lambda is in hours and our time is in minutes, we have to go and we break this down and then we multiply it by lambda. So it's not that different. Like I said, normally before we'd break down lambda down to minutes and then multiply it by the t. Well, I think that there's an advantage when you're teaching this, and this is a new topic to people, and showing them how the unit conversions work. And so I started looking at this a long time ago and playing with different ways to do this, and I kind of think that this is the easiest way. The other thing is I have a nice table that shows how this is all related, which I'll show you in just a sec. Okay, so let's start putting in the numbers. So 3 minutes, and this is nice because we don't have to convert anything up front. And then 60 seconds, that's for that conversion. And then 15 is our lambda. So in the past, when I was teaching the exponential probability distribution, I'd convert the lambda into something, and they'd say, where did you get that number? Well, in this case, I think it kind of makes sense a little bit, and I'll show you why. So let's work out the answer. The answer, or almost the answer, is, at least this whole e part, is 1 subtract 4, 7, 2, 3, and that gives us the answer of 0.5276. Okay, so we'll say that's our answer for the problem. Now, I want to show you that table that I was talking about real quick. And I'll link this table in the notes for this video. So this is a table that I made up, and there's three there's actually 6 tables, I guess, but there's 3 pages, and each page has exponential probability distribution table for time and for distance, because sometimes things have to do with, say, tires. Like say tires wear out in relation to miles, and say they wear out following an exponential probability distribution. So in that case, we're not using time as a measurement, we're using miles. So it's a little different, but it's still the same thing. It's a unit of an interval, and that's where we can apply the exponential probability distribution. So, okay. I'm going to zoom in just a little bit. The white balance will come back. Okay. So in this case, this is a value greater than 0 to infinity. This is a type of table that's set up for a certain type of question, which we're going to have one in just a sec. But we have these different conversions in there. So this one says per hour to seconds, per hour to minutes, and then hour. You see there's no unit conversion, okay? And so none of these have a unit conversion, and that's because they're the same, day. And so that's kind of how this works. On one of the other pages, it'll be the 0 to a number. See, this one is a number to infinity. So this is in the tail portion, and it says more than a specified interval, none until a specified interval, meaning none until a certain value, and then whatever after. So on this one, there's no 1 subtract the equation, and that's just the way this is because of the part of the tail. Then down below, we actually have the distance part, and then it shows the tail, or where we're looking at, where this calculation works. So ours is, let's see, ours is this one. And the one that I used for this, and like I said, it's not rocket science, in that I think the only thing that I've done that might be a little different is I put together a table of these values, and I think it's useful. And so this is the conversion. It has, it says up top, will arrive in 0 to a certain interval, and then it says in our question, I think it's in a certain amount of time, in 3 minutes, meaning 0 to 3 minutes. So for ours, the rate was in hours, and the t was in minutes. So this is the equation that I wrote out. And that's essentially what we solved for. And what this means is we're solving for this left curve area, okay? And that's why we subtract our calculation from 1. I'm going to go back to the other preset. Okay. So as the picture showed, the probability we're solving for was kind of like, that's not a very good one, but for this area, okay? And that's because it was a 0 to something, meaning in 3 minutes. Okay, so for the next one, it is more than 7 minutes. So the more than 7 minutes means at 7 minutes, it could be anything more than that. So, but it doesn't start until 7 minutes. So that is a one where it's going to start halfway into the distribution, and then it's going to be all the way into that right tail area to infinity technically, because it doesn't say that there's any stopping range. So the calculation for that one is this. Like I said, I'm going to link these files, and I always link the notes. Some of my older videos I've been redoing, and I started scanning all the notes, so I'm just trying to get everything up there so somebody could download them. I was even considering in the future making up sample or practice questions that are just like the videos so that people could download those and try them. Okay, so this is what the formula is for this one. Notice when it says more than, When it says more than, we are not subtracting our equation answer from 1, okay? So more than, we do not subtract from 1, so I'm going to fill it in now. And then our answer ends up being okay. And like I said last time, this actually will kind of go on to a point, but it's going forever. The area that we're working with is over here. Okay. And then the between. The between, I've seen different formulas, and technically you can almost do it different ways, but the between's easiest doing it this way. Just trying to make sure that I'm not off the screen here. So the between is, so between 2 to 4 minutes. Okay. So the between is, we do it just like we did with the more than 7. So it's the easier equation. And this one I write with this. I say t, and then I do a little lower, I do a subscript little l, meaning the lower limit. And then we're doing this 60 conversion only because of this specific question. We don't do that all the time at all, but because we have lambda, we just left lambda in hours, and we're doing probability for minute calculations. We have to do the conversion, and then lambda. So it ends up being this. Oh, sorry, I only did one side so far. That's okay. It ends up being 2 by 60, and then 15, but I need to fill in the rest of this. This one would be t, and then I do a superscript, subscript u for the upper limit. So there's a lower limit, upper limit, and that's the only difference between these two things. And then 60, and then lambda. Okay, so on this one over here, it would be e, and then it would be t. Sorry, it would be the upper limit would be 4. I'm sorry, I'm in the demo mode here. 60, and then 15. So we have 2 over here, we have 4 over here, and this is the actual formula. Okay. And then we just go, and I'm going to write down the 2 calculated numbers. Oh, and I mentioned in the other video, but I don't think I mentioned it in this one. Whenever you can in your calculator, use the e that's in your calculator. And because now e is the natural logarithm log, and e stands for, it's a constant, and it stands for 2.718, but it actually goes on forever. So I recommend at least going out 4 decimal places if you're going to hand type it in. But your calculator is going to be more accurate because it goes on a lot further in your calculator. So then when we work this out, our answer is 0.2387. Good, I'm still on here. And the part of the distribution we just solved for, really small, is the in-between area. Okay. Now I want to show you that table a little bit more that you can download in the links for this video. So this was the will arrive in type of calculation that we're looking at. And you see it has time and then distance. Standard distance, I guess, not metric. If I had a request for metric, I could make it for people, but this is kind of more of a teaching tool. That's why I made it. And then this shows the part of the curve. the other big thing is this shows the relationship between units and how the conversion works. Like I said, you could do what they call an exponential parameter, and you go and you convert out everything and then just kind of plug it in. But I end up with a lot of questions going, where did you get that value? And so this actually really lays out how the units are related and where all the values can and should go. And then when they are in the same units, you don't have a conversion factor. So hour, no conversion factor. Okay. And then the last one, really small print. I'll zoom in some more. The last one has the L's and the U's for lower and upper, lower, upper. And that's all that you do there. I had to go really small to fit it on this page. And then this one. This one, didn't have to go as small. And this explains the lower limit, upper limit, and then kind of shows the picture. So I hope some of this helped with the exponential probability distribution. And in summary, I want to point out one thing real quick. The typical formula that I use if the units are the same no matter what they are is a formula like this. Because if they are in the same units, you can just go and just do the division work instead of, see, if they're in the same units, you don't have to go and convert your lambda down to the same as the time. It's in the same units, and it makes it really easy. And so it doesn't really matter. The other nice thing about the table is if you need to go and convert to a different unit that's not listed, the table kind of gives you the understanding of how you would do that. Technically, you could go out further and further, but as you go out further, and as you're doing conversions away from multiples of units, your probability gets so small that it's kind of pointless to do that because the probability is so tiny. So, well, thank you for watching.